The second part of this module's discussions are going to focus on moisture. All right, moisture affects pilots tremendously, and it causes weather. Without water vapor in the atmosphere, a lot of what we know as weather would not be occurring. Water vapor is a gas. It takes the form of water and tasteless, but water vapor, you can't, if you have water vapor in the air, you're not seeing it. It doesn't, and when you begin to see it is when it begins to become water droplets. They may be very, very small initially, but they'll gradually form, typically form into clouds, maybe even into raindrops. All right, and the key thing with the atmosphere is it can freeze water. Atmosphere has a temperature range that actually corresponds to water being in a vapor, being in a liquid, and being in a gas, an ice or solid state. So let's take a look at that a second here. It's really one of the key points of this whole thing. Let me get over here a minute. All right, here we go. So let's start with water vapor and evaporation. In order for water vapor to evaporate, you must take away some heat. It must be heated. Water heats. So it takes some heat to change a liquid into a gas. All right, it takes some heat to change a solid into a liquid. So now we know that if you want to change ice into water, you've added heat. If you want to change water into water vapor, you've added heat. Well, the other thing that occurs, so in the whole evaporation or ice to water vapor process, heat has been added. Sun's radiation, however that heat got there, a big factory pushing out hot air out of its stack, whatever, that's causing all this to heat up, that air to heat up, that causes evaporation, that adds water vapor to the air. One of the other things I always found fascinating about sublimation in ice is I can remember growing up in Pennsylvania and seeing ice on the road and knowing the temperature outside was in the single digits sometimes, and yet that ice seemed to go away as the day went on. What was happening was sublimation. I had a great bright sunshine, even though the temperature wasn't warm enough. That surface was, and that surface wasn't necessarily melting, it was sublimating. So that ice literally was transforming into water vapor in the cloud eventually. All right, now that you've got the water vapor here in the cloud, we'll say, what happens to it? Well, remember, air cools as it rises. So if air cools, what's happening? You're taking away heat, and there's condensation that's going to occur. You pulled heat out of the water vapor, and a liquid forms. Oh yeah, you pull more heat out, the higher it gets, and ice is going to form or freeze. So there's three processes here. So we take heat in. Latent heat has to be absorbed by H2O, and it's called latent heat, or latent heat has to be released by H2O. So as the water vapor condenses, latent heat is released. Oh yeah, you've heated up the atmosphere around you. That's going to have a big impact on your stability of that atmosphere. Just one of the things to happen. Oh yeah, and if you go from water to ice, more heat's been released. So again, it's going to be warming the atmosphere. So there must be other processes taking place to cool it. All of which are big factors in how clouds form now. So now that we've got a little bit of an understanding of this, we just talked about all the changes of state. Look at a cloud. You see the bottom of that cloud? There's water vapor there because there's nothing happening. And then once your cloud starts forming, there's droplets in there. Not all clouds produce rain. Matter of fact, not many really actually, the overall number of clouds that are in the sky produce rain. Oh yeah, and the higher up it got, then you got more latent heat released, and you're getting ice up here in the anvil of this cloud. So you can see the changes of state as the water moves up through this whole cloud. So with that, one of the ways to measure moisture in the air is vapor pressure. Vapor pressure is just a pressure of any gas. Each gas, individual gas, nitrogen, oxygen, exerts a pressure. If you sum them all up, that's the total atmospheric pressure, which we've learned earlier. Well, water vapor exerts the pressure as well. There's another important fact is an air parcel can only hold a certain amount of water vapor depending on the temperature of that air parcel. So if that air parcel has a really warm temperature, its saturation vapor pressure is pretty daggone high. It can really take a lot of moisture in. But if that air parcel is really, really cold, like in the wintertime a lot of times, can't take a lot of moisture, saturation vapor pressure has gone down. So one of the key things to remember here is saturation vapor pressure is changing depending on the temperature that air parcel has. Now, vapor pressure is just the amount of water in the air. So it looks at comparing that vapor pressure of the water to the actual saturation vapor pressure, what amount of water it would take to saturate it. And that's how you get relative humidity. We hear relative humidity all the time, and it says, oh man, the relative humidity's high today, it's 80 or 90%. But if the temperature was 30 degrees, the saturation vapor pressure would be relatively low, and so would the vapor pressure to make it 100%. It would still be relatively low. But look at Florence. The air temperatures are in the mid to upper 70s, and the saturation vapor pressure is really quite high. Even though we're getting 100% relative humidity, the amount of moisture, the amount of vapor pressure of the air, of water in there is huge. So just something to think about. Another measure is dew point. And this is what's reported on the METARs. The higher the dew point, the more moisture is in the air. Not necessarily how much compared to relative humidity of the air, but more moisture is in the air. The dew point depression is the change in temperature between the temperature and dew point. That value. And it's kind of key. If you're looking for fog at night, for example, and you knew the temperature was going to cool at night, the closer these two get to each other, the better and better chance that fog is going to be forming where you are. The further apart they are, the less that chance might be. And the higher, and another thing in wintertime, for example, a lot of times meteorologists will look at the temperature and see, oh, the temperature is 34 degrees, dew point's 15. It's supposed to start precipitating soon. Well, look at that temperature, dew point, pretty big range. You bring moisture into there, that temperature is going to begin to drop. And all of a sudden, it's going to wind up closer and closer to the dew point. So that temperature might go from 34 to 28. And you wind up having ice or snow instead of liquid. So it's just something, a wonderful value here to use, the dew point depression. I wanted to show you a little bit lapse rate and stability with this moisture added in. And I think I'll use that over here. So right here is that sounding, another sounding. Down here, it's pretty dry. Here's dry adiabatic lapse rate. Temperature is almost mirroring it. The air parcels are going up. The actual environmental air is quite dry, quite there. Well, say this temperature, all of this water vapor got pushed into the air right about here. And all of a sudden, this air parcel became saturated. Well, we know that that air parcel is now being pushed upwards. So what's happening? That air parcel is saturated and it's cooling. It's producing a cloud. Droplets of water are forming. Oh yeah, it's also releasing heat. So instead of cooling at this rate, the dry adiabatic rate, it's cooling at this rate, the moist adiabatic rate. So it winds up to the right. It's warmer than the surrounding air. It's going to accelerate upward very quickly. So if you have looking for thunderstorms or whatever, the more warmer the moist adiabatic lapse rate takes it compared to the actual environment air, which is over here to the left, the better chance there's going to be convection. Now, look over here. This is the moisture, the dew point. This is actually a plot of the dew point. You see this? That's really, really dry. It's way, way over to the left. So it's not going to be getting any clouds there. There's just no way you get enough moisture unless something was bringing moisture in, moisture advection. So this is just an example of how moisture looks in the atmosphere, what you can do with stability with moisture, how it changes. Moisture changes stability. So I wanted to show a little bit of vertical motion and moisture and just how it works. This is Florence. All right. Florence is tremendous amount of vertical motion in it, obviously, and the winds are flowing around it. This is 700 millibars, so it's, you know, a third of the way up through the atmosphere. Probably around, about 9,000 feet probably would be a good estimate. It's a good level to look for moisture too. It's got lots of moisture here. The green is the moisture. So as this thing moves forward here in time, notice these blue. These are what they call omega, but it's also vertical motion. It's just another term for it. You can see starting to get some lift here on the mountain ranges. You're really being able to start to see. It really focuses right on some of the ridges and stuff here. That's your vertical motion that is occurring just because all this air is getting pushed into the mountains. You'll notice that the amount of precip on the other side of the mountains is much less. The heavier precip's closer. Oh yeah, look out in the west. You can see the mountain ranges of all triggered vertical motion. Here's the Sierras. Wow, look at all that vertical motion there on the Sierra Nevadas coming up there. So your air is coming in off the Pacific. Not much moisture with it, thank goodness. But you are triggering a lot of vertical motion. So one of the ways to just look at all of this to see how it corresponds to what's happening is looking at radar. And you can just look down here. Wilmington's out today. Surprise. But just looking at the radar, even down in Texas, we'll say, you can see the moisture. This is where vertical motion, and this is where the stability is playing a role, probably causing this to go up more because it's a very moist sounding. I wanted to show you one other sounding here. We'll go back in time, I think might be a better thing. And there we go. This is Morehead City. Look how moisture sounding is here. Tons and tons and tons of moisture. The green line's almost right on top of it. They had a tremendous amount of rainfall down there, as you can know. So this is this morning sounding there. You can actually see all the moisture just pouring up through this atmosphere. Oh yeah, because it's so daggone moist, it doesn't take a lot to become unstable. While it's not tremendously unstable, the moist adiabat's not way, way over to the right, it is unstable through a large, large area. Because there's so much moisture and that instability there, you're getting tremendous rainfall out of it as well. So, another place to look with the weather sometimes is just looking at satellite, and you can actually see the images here. So we'll go back to a couple satellite images. And see if we can look at a couple things here. Just to look at where moisture is going. Sometimes there's a product called water vapor. Here's your goes east. Okay, water vapor is actually a measure of the amount of water vapor in the atmosphere, and it looks at it roughly between 10 and 15,000 feet up. So this is the greenish area is very high concentration of water vapor. Look where that water vapor is coming in from. All the way out here in the southeast Atlantic, all the way up. It's just flowing like that. We'll just loop this. And you can actually see the moisture coming up into this circulation right here and getting outflowed from it as well. But there's a lot of moisture. Here's the same happening down here in this semi-tropical feature as well. Oh yeah, here's the dry air. Lots and lots of dry air around. So sometimes you can actually see dry air work into these circulations. Like you can see here, a little bit of dry air has come into Florence. And you can actually estimate that maybe that is causing a slight problem to Florence as well. So now that we've covered moisture, let's look at a METAR. We'll just pick, one that's nasty weather right now. Greensboro. Couple things this week. You're going to be looking at visibility right here. Right after wind, the very first column is visibility. 10 statute miles. That's the surface visibility determined by ASOS there. Overcast, 900 feet. Remember, there's three digits right here, 0, a 0, and a 0. Add 2 zeros to whatever you see. So if you have 900 here, put a 1 there, that'd be 1,000. Put another 1 over there, it'd be 10,000. So that's your height in the atmosphere. Dew point. Temperature comes first, dew point comes second. Dew point's 23 degrees Celsius. It's about 75 degrees. So all of a sudden now you can see that, wow, you've got really a lot of moisture in the air. But look at them. They're right next to each other. 100%. It's saturated. Rainfall, right here. This is since the last observation, amount of rainfall. And if it's on the hour, it's the last hour rainfall. But you had 7/100ths of an inch. And you can see each one of these is 100th. So there would be a 10th if you had a 1 there. There would be 1 inch. And you can even get 10 inches in an hour if you can see one that fast. So, and this is the last 6 hours rainfall here. 6. So it's 1,500. So they haven't had a lot of precip at Greensboro yet. All right, so let's take a look at how about Oklahoma City. One of the things I wanted to show you in clouds here is a few at 4,000 feet. All right. So now we know a few. We have scattered at 5,500. All right. One of the keys to things is they add. So the amount of cloud here at 4,000 feet adds to whatever amount of cloud was at 5,500 feet to make the scattered. Now you keep adding those two and you wind up with broken at 7,000. So each one of these contributed to the total number of cloud, the broken that you see here. So it isn't just one, each individual that, 7,000 was where it was broken. No, it was the few, then the scattered, then the broken. So as you look up, you're being more and more of the sky is being blocked by clouds. This is the least amount. This is the second most, and this is the most. So they add up cumulatively. So hope you got some understanding of moisture and stability now and how you can measure them and all. Oh yeah, one of the other things is look at a surface observation, the value under the temperature. Here's temperature on the left. Here's moisture, dew point right there. So you can see here this 3-degree dew point depression. Not a lot. Look out in Las Vegas. Downslope winds here, 80 degrees, 34-degree dew point. That is dry air. Very dry. So you can see the dew point depression there is what, 46 degrees. So very, very dry. So hope you got something out of this. Let me know if you have any questions.